Okay, so I think people are having a nice leisurely lunch, but welcome back. So I got through most of lecture 2, and I really didn't expect to get through all of it. Oh yeah, would help if I was hooked up here, which is where. Okay, so as I said, I was not sure I would get through, I was pretty sure I would not get through lecture 2. So we're going to finish lecture 2 and then move on to 3. And this works out good for my organization because 4 is a little short, so it's perfect. So I was discussing, first of all, the importance of this microstructure as a ubiquitous microstructure for what we see at the finest scale during transformation. In these crystalline phase transformations, especially in the reversible case, and I said there's some. So so the point is you realize suddenly that when the compatibility of the phases has a not only effect on the microstructure, the appearance of microstructure, but it really matters for the behavior of the material, particularly the hysteresis. Once you know that, you can go do many easy things, and this is maybe the most obvious one to do, is you can look for stronger conditions of compatibility in other cases, in particular in this calculation. So that's what we're going to do. So recall this microstructure. There it is. Whoop, a little bit weak. And it was governed, let me remind you about the algebra that goes behind it. First of all, there's this so-called twinning equation that governs the compatibility of these interfaces. And then there's another equation which governs the reduces the transition layer energy in here to 0, or to as small a value as you want by making these finer and finer. And that's governed by this equation. So that's the algebra of this behind that. And then there was a side issue, which is not so unimportant. It's quite important. Is that, of course, the microstructure is not infinitely fine. And then there's a competition, essentially, between the interfacial energy on these boundaries and the bulk energy in this transition layer. If you include branching, as we said, then there's the competition is a little bit different. It's between the a more delocalized bulk energy, an elastic energy which extends over a much larger region, and interfacial energy on these bands. And in some scaling regimes, the branching is preferred, and apparently it's preferred in this material because we do see the branching. And in other cases as well. It's not so uncommon, but we don't always see it, of course. So are there any additional hidden accidents on the lattice parameters that could make these two phases more compatible and therefore even further reduce the hysteresis, maybe improve the reversibility? And there are. So it's a matter, from a mathematical viewpoint, of looking for degeneracies in equations. So here's a set of algebraic equations, and let's look for degeneracies. So let's suppose this one, if I pre-multiply and post-multiply by UI inverse, and then use the polar decomposition theorem, this can be put in the form of the previous equation, previous lemma, with about lambda 2 equals 1. And so let's imagine that this has been already satisfied. We have 2 solutions of it. So we suppose we've done that. And then let's focus on this one. So how would you satisfy this? If this has been already satisfied, that means the R is now known. And then the unknowns here are the volume fraction F. That's the volume fraction of these one set of bands versus the red bands versus the blue or green bands. This is an unknown. This is a rotation matrix, and these two vectors B and M. So in Peter's notation, B tensor M would just be written BM. So anyway, that's different notations. Okay, so what do you, if you want to solve this? Well, first thing you do is you substitute for RUJ. That's UI plus A tensor N. Then you get FUI plus 1 minus FUI. You get UI plus FA and tensor in there. So it's a little bit simpler. And now, if you want to solve an equation like this, again, it's a lambda 2 equals 1 thing. You know, you have rotation times stuff minus identity is B tensor M. You just have to imagine taking the polar decomposition of this quantity, and then the stretch, the rotation, the polar decomposition could be lumped in with this unknown, and then the stretch tensor in the polar decomposition is the thing that you would like to have whose middle eigenvalue is 1. That would be necessary and sufficient that this has a solution. Well, instead of calculating the polar decomposition of this, you could calculate the square of the polar decomposition, or the square of the stretch tensor, and it's just this. And of course, if the stretch tensor has middle eigenvalue 1, then this has middle eigenvalue 1. So the whole point comes down to finding a volume, and we've eliminated now the R, that was the whole R hat, that was the point. So now it comes down to finding, can we find an F such that the middle eigenvalue of GF is 1, and then we have the existence of this microstructure. Okay, we can write a minimizing sequence. So let's look at the algebra of that. We want GF minus identity. So we want this GF to have middle eigenvalue 1. So the natural thing to do is subtract identity, and then we want that to have middle eigenvalue 0, right? So we might as well take the determinant of it. So that's, and remember, GF is quadratic in F. So you have something quadratic in F, you take determinant, it looks like a 6th order polynomial. So we need to find the roots of a 6th order polynomial. Okay. But actually it's not a 6th order polynomial. If you're familiar with these rank 1 tensors interact in some very nice way with determinants. And so, in fact, because of all these rank 1 tensors, it looks like a 6th order polynomial, but it's actually quadratic. And it's symmetric about a half as a function of F. So it basically looks like that. And we're looking for roots of this. Now, if we find a root of that means one of the eigenvalues of GF is 1. It doesn't mean it's the middle one. We need the middle one. So there's some hidden inequality in here as well. So we'll have to deal with that. But to start, we look for roots. If you take measured lattice parameters of some martensite which is not reversible, for example, a martensite in steel, take the measured lattice parameters and stick them in and calculate this quadratic function, it may well look like this. So not every martensitic material has austenite-martensite interfaces. Okay, so and typical non-reversible martensite may well not have a root at all. Okay. This material, of course, has a root, as you can see. So it looks like that. So it's, in fact, by the fact that this quadratic function is symmetric about a half, it has 2 roots, F star, 1 minus F star. And then, of course, you do have to worry about whether the eigenvalue you got is actually the middle one. So there's an inequality, and you can write that inequality down. I won't write it down. Often it's satisfied, but you have to check it. If that's the case, then going back to the lemma, for F star, in fact, we have 2 solutions, because, in fact, we had 2 solutions of that lemma. So it's a very similar situation. And for 1 minus F star, the other root, we have these 2 solutions. Once again, as I mentioned before, if you take one of these solutions, I don't remember which one it is, you compare with this picture, all the geometry agrees very nicely. The only point is about the fineness, and as I mentioned, all the geometry is predicted nicely by this calculation. What happens when lambda 2 is 1, not lambda 2 of GF, but lambda 2 of the original stretch tensor? Of course, then the quadratic function looks like this, right? Because it's at volume fraction 0 and at volume fraction 1, those are the pure variants, untwinned, which would be compatible in that case. So in the case that the individual stretch tensors have middle eigenvalue equal to 1, the graph of GF minus identities looks So in that case, of course, you have perfect interfaces, and you have 2 here, and you have 2 here, and those are the cases, those 2 and those 2. So that's the case. That's a generic lambda 2 equals 1 material, like I was showing those low hysteresis materials before. Okay, so that's fine. Now, if you're looking for degeneracies, you know, it's so obvious. What do? I mean, why not have a quadratic function which is symmetric about a half be identically 0? Why not? Okay? When I first said, okay, this should be possible, then I said, in my mind, I said, no way any real material's ever going to satisfy this. But true enough, I start calculating, real materials do satisfy this condition. So let's first write the condition. First of all, you can imagine to make the endpoints roots, you have lambda 2 equals 1, and lambda 2 is now the middle eigenvalue of U1, let's say. And then if you have a symmetric quadratic function which is symmetric about a half and it's identically 0, then you might as well, necessary and sufficient conditions are that the derivative is 0 there. That's the derivative. So there's the conditions. Lambda 2 equals 1 and this second. And these are called the cofactor conditions. Of course, you know, so every point along here gives a solution of the crystallographic theory. In other words, you can continuously change the volume fraction, and you can, for each volume fraction, you can write a minimizing sequence which drives the energy to 0. So that's more compatibility, right? So that should in principle be useful. And I should say, in all the results I'm mentioning in this talk, the conditions were written before the experiments were done. So these are not after somebody found some interesting alloy and then go back and try to figure out why, but it's really, this is driving the material science and the material synthesis. Now, of course, at every point in here, a middle eigenvalue of GF is 1. An eigenvalue of GF is 1. We also have an inequality. And if we want every single point along here to the eigenvalue, which is 1, to be the middle one, you have to satisfy that inequality. Necessary and sufficient. Okay, very good. Okay, so here's what it looks like. So of course, so any volume fraction satisfies the crystallographic theory. So we have the volume fraction 0, you get the single variant. That's because of the endpoint. Of course, the other endpoint gives this one. But then you can continuously vary the volume fraction. And perhaps I overdid it I exaggerated. This is not a realistic material. I exaggerated the transformation strain so you could really see. But you know, there is a vanishingly small transition layer in there. I think I used linear interpolation for the transition layer, so you can see. But in a way, this should be, this should be useful for a transforming material, because there are many. If you compute the strain ellipsoid as you move along this increasing f, it's going from this strain ellipsoid to this strain ellipsoid. So this is not compatible with this because it doesn't deform when you change the volume fraction. It deforms a lot, but it deforms in such a way that it always has a compatible interface. And now, this is with maybe variance 1 and 2, but if you satisfy this for variance 1 and 2, you've satisfied it for all pairs of variance, okay? So that looked like pretty interesting conditions. Here's some cases. Now, we had those 6 energy wells. So, in fact, these pictures are, let's just take this applies more generally, but imagine we had those 6 energy wells. You could write them as energy well 1, variance 1, 2, 3, 4, 5, 6. 1 and 2 are so-called compound twinned. And that has to do with the geometry of the twinning of these 2 variants. I'm not going to explain that. But in any case, if the cofactor conditions, it does depend on the twin system. So if you satisfy them for these compound twins, it looks like this. And in fact, there's a transition layer in there you can't see very well. It's actually a plane strain situation. And again, there's this classification of twins that I'm not describing, but if you satisfy them for type 2 twins, that's other choices of the variance, then then it looks like this. In fact, the austenite-martensite interface is parallel to the twin boundary. Of course, that's very good. That's very good in a sense because there's no transition layer at all there. It's completely zero energy microstructure. So that seems that attracted our attention. And actually, this is from Sherry Chen's thesis. She noticed that for type 1 twins also, you could completely remove the transition layer. So these are deformations. In fact, they can be large deformations in which there's a big shape change in each part, in the 3 parts here, but they're all fitting together perfectly. And there's no transition layer here. Of course, when there's no transition layer, you completely remove this competition between bulk and interfacial energy. That should be a very good thing. And then, of course, once you get on this boat, you can think of curved interfaces. These all have zero elastic energy, and illustrate the many ways you can fit together the phases without having transition layers, without having stress. This is a nucleation mechanism. So this is the red is austenite, and on a corner you can nucleate 2 variants of martensite, and you again have no elastic energy. This is a case with 2 variants of martensite. So this is a green variant, and this is a blue variant, and so it's all martensite. And then you can nucleate a little region of austenite and grow it up from 0 volume inside that band. So again, many different ways of fitting the phases together. Here's a much more complex way. Again, this has no elastic energy in this picture. And in hindsight, we realized that maybe the complete elimination, and this concerns a whole slew of open questions, but we began to get the idea that it's really complete removal of the elastic transition layers may be the most important aspect of compatibility. So we call that supercompatibility. That completely without stress transition layers. So if you satisfy these cofactor conditions, you have many interfaces which are low energy interfaces in the sense of the crystallographic theory, ordinary crystallographic theory, but you also have many cases where you can completely remove the elastic transition layer. And in these materials, there are always, no matter how clean you make the material, there's always non-transforming defects in the material. And to accommodate these, it can be quite useful to have these different ways of fitting together the phases. For example, around a non-transforming defect which is relaxed in the austenite phase, you can use these microstructures to make a bubble around that of a certain, a bubble of austenite, which doesn't transform, but it's only a small region and is completely compatible with the martensite around it. That can be very useful. Although, I'm going to show you some graphs of some materials that were designed to satisfy the cofactor conditions. We have 2 materials now. And the exact connection between these conditions and, and the reversibility of the phase transformation is an open question. Okay, so as I say, there are 2 materials that satisfy the cofactor conditions. One is zinc, gold, copper, and the other is a complex alloy in the titanium-nickel system. This one was found in my lab when we just did, like I said we did with the lambda 2 equals 1. We found a good starting point, and we just systematically changed the composition till we satisfied both these conditions, lambda 2 is 1, and this cofactor condition that I mentioned. It's, by the way, Sherry Chen's thesis, who's an organizer of this program, or the whole year, or the whole spring program. So here's an this gives an example of hysteresis. So this is calorimetry. So you're changing the temperature and measuring the heat flow into the specimen, and every time you get a peak, that's the signal of a phase transformation. And the area under the peak is the latent heat of phase transformation. Standard measurement people do, and we do with phase transformations. And you can see from this difference of these peaks on heating, this is on heating and this is on cooling, that they're quite close. But in fact, it's really, it's even better than just pure lambda 2 equals 1 materials, because this material, this is the one that most closely satisfies cofactor conditions. That's a measured 0.2 C hysteresis. This is a big first order phase transformation, like 7% transformation strength. And the other thing is, these nearby alloys, like this one, it's just very close to this one, 28 or 20. We did quite a few tests on also 27, which is not listed here, but a very nearby composition. It's just an ordinary martensitic material. No special behavior, no special hysteresis. So again, it's very dependent on composition. So it's fun to look at what it looks like when you transform. So this is a thin plate of the cofactor alloy. That's the martensite. It's being heated and cooled. That's the austenite, and it was being heated and cooled in such a way to try to make as uniform as possible a temperature. Of course, it's not easy to do that because it has such small hysteresis. There's bound to be some biasing, and that's why you see that the interface moves more or less diagonally. Like liquid crystals, these are low symmetry crystals, so if you look at them under polarized light, you see lots of nice colors. Each color represents different variants of martensite, and the striking thing about this video is that every frame is different. So that's very unusual in martensitic phase transformations. So, the standard thing is every frame, it looks exactly the same. In fact, there's a concept called return point memory, which is based on that concept. So it seems that because of all these additional compatibility conditions, somehow the material really doesn't know how to get started, and each frame is different. But I don't have an explanation for this in any. You could argue the other way. If the energy landscape is so flat it doesn't know where to get started and it goes in any path, then why don't the defects in the material, like you see, why don't they bias the material more than an ordinary material? So it's completely unclear why you get these different. But we've gone into individual microstructures and tried to understand, make sure the cofactor conditions are satisfied, and we see but they're significantly more complex than the ones I showed earlier. I thought this would be interesting. Is it going? Good. This is a grain boundary right there. So of course it's very interesting what happens at a grain boundary. So this is one crystal of the material. This is a differently oriented crystal of the material. In ordinary martensitic materials, we would see a band of martensite come against a grain boundary, and then another band go off at another angle. That would be a very typical thing to see. In this material, you see. First of all, you see every frame is going to be different. But the other thing you see is that it seems that the microstructure on one side of the grain boundary is uncorrelated from the microstructure on the other side. There's no obvious relation anyway from the pictures of the relationship between the microstructures on each side. Again, indicating there are just many, many choices, and indicates roughly that there's a very flat energy landscape. Good. Here's another. This is it's always more demanding to to stress-induce the phase transformation. So this is something about this is something that very much has to do with in the first lecture. I had this energy of the loading device. So you have this variational problem. You minimize the free energy of the material, but if it's being loaded, of course, as Gibbs would say, you have to close the system, include in your system also the energy of the loading device, and minimize the sum of those. And so because of that, you have an effect which is a well-known effect. It's called the effect of stress on transition temperature. It's the analog of the fact that when you take water and you take it to the top of a mountain and boil it, it boils at 90 degrees C instead of 100 degrees C. And of course, if you do, and in fact in this material, pressure would have almost no effect on transition temperature, but uniaxial stress has a huge effect. So this was done. This was done by taking a bar of this material and stressing it until it transformed, and then letting go. And this you would get curves like this. And they were done in this. They were done at small scales, mainly because it's quite easy to do it. So this is only 1 micron. This is a 2 micron diameter pillar, and so you can see how it deforms. Is it doing anything? Is it deforming? Look at the top. No. Let's see. Okay, there it goes. So if you look at the top there, that's actually coming down. And one thing that's quite unusual about this, at these scales, an ordinary martensitic material would show a big fat band of martensite across the middle. And here, there's microstructure which is at a much finer scale than even micron scale. So that means that somehow you're paying so little for the interfaces that appears to deform homogeneously, even though it's full of microstructure. And you can see it's got great reversibility. I mean, this cycle 1, and there's cycle 100,000 there. This part is nearly the same. There's a little bit additional not softening, but hardening with 100,000 cycles. And you have to keep in mind that these are very transformation under stress is very demanding, much more demanding than in the energy conversion devices we'll discuss, which has no stress. This is transforming. It's about 6 or 7% strain, and this 300 megapascals. I guess it's going up to 700, 600, 700 megapascals. If you're not familiar with those units, that's a lot of stress. For example, in this building, the steel that holds up this building, or even a taller building, the yield stress of this steel, in other words, the failure stress of this steel would be somewhere around here. So at each cycle of 100,000 cycles, it's getting a lot of stress, and it's reversible. So that's quite unusual behavior, both in the hysteresis and the reversibility. Okay, and there's a little model of the microstructure that we think is there. This one is in some ways even more spectacular. This is found by Eckhard Quandt in Kiel, Germany. And it's an alloy of titanium, nickel, copper, cobalt. Here it has some composition, again, some far from stoichiometric composition. Okay, so you see those indices indicating the composition, and you see its behavior. Now this is the behavior of our ordinary phase transforming material. This is cycle 1. Already by cycle 10, we have some plastic deformation. The hysteresis loop has gotten elongated. More plastic deformation by cycle 50. This might last 500 cycles, and then it would break. Now look at this alloy. So again, it's compositional sensitivity. So this number is pretty close to that number, and this number is pretty close to that number, and so you see all these. This is quite close alloy to this, and with cycle 200, it's nearly the same. But it's much more spectacular than that, because in this graph, again, it's 400 megapascal stress each cycle, and the black curve represents, and it's full stress-induced transformation. The black curve represents cycle 1, and the red curve is cycle 10 million. So that's what we would need for energy conversion devices. So, this geometry, just the way the phases fit together, has a profound effect on not only the microstructure, but the properties and the reversibility of the material. Okay, very good. Okay, so now we start on lecture 3. Now, one thing I didn't say is there is a theory of how compatibility affects hysteresis. How lambda 2 = 1 affects hysteresis. So I was I actually wanted to lecture on that, but I didn't have a chance. So if I can tell you more about that, and I'll provide some references in the documents we're supposed to write at the end of these lectures. So, oh, there's some weird, okay, some bad fonting there, but so now we're going to begin to talk about energy conversion, and I divided it into two parts. One is the ferromagnetic case and the ferroelectric case. We worked on both parts. We kind of soured on the ferromagnetic case for reasons I'll tell you. And so this involves phase transformations in which in the ferromagnetic case, one phase is a strong magnet and the other phase is non-magnetic. Okay? So, and some of these transformations, you can make lambda 2 very close to 1, so you can have quite low hysteresis. You can have examples with, I'll show you some examples later. There's sort of three important transformation temperatures in a way, because if you just have a material that's just a ferromagnetic material with no phase transformation, you'll reduce the temperature. There'll be a certain temperature, which I'm calling TCA, which is the temperature at which it becomes ferromagnetic. And that's a second order phase transformation, so there's no jump of the lattice parameters at that transformation. And then the strength of the magnetization increases as you lower the temperature. So that's the Curie temperature of, and it can be different for the two phases. So now you have a question of, what are all the possible behaviors, and you can dream up many. All of these, in fact, are seen in real materials. So again, I make the temperature axis vertical, and so you imagine this is an austenite phase, and we're going to consider the case with a phase transformation, of course. So what could happen is you could first ferromagnetically order. So I draw a kind of schematic domain structure picture, and then you could have a phase transformation. And the Martensite phase transformation temperature could be, Curie temperature could be above, so you could transform from ferromagnetic austenite to ferromagnetic Martensite. Typically, the length of the magnetization is the main vector field you're interested in that case, and it could also jump. I didn't really draw it there, but it could change abruptly at the phase transformation. Typically does. You could have this situation. You could have austenite ferromagnetically order transform to Martensite that's not non-ferromagnetic, and then later, because this has very different lattice parameters from this, it could decide to ferromagnetically order at a lower temperature. We have examples of that. You could have a material which is ferromagnetically orders in austenite, transforms and loses magnetism altogether. And you could even have a material, I'll show you one very interesting material, in which it has no ferromagnetism at all. Okay? So, but secretly, the austenite phase, if it could be, if it did not transform, this austenite phase would have ferromagnetically ordered down here somewhere. Okay? So that could be true. You just don't see it, right? I mean, that's the thing about big first order phase transformations. They can mask many interesting behaviors. So I'll tell you about that later. The important thing is these second order phase transformations. They can't, at least to first order, if you apply a magnetic field, they don't change. But this could be quite sensitive to a magnetic field, particularly in a case like this where one phase is strongly magnetic and the other is non-magnetic. So we'll exploit that in the energy conversion device. Okay, so this is a general slide about the sensitivity of properties to lattice parameters and why, therefore, in a first order phase transformation you can have this dramatic changes of properties that I've showed there. Okay, we don't need to worry about that. Okay, let's see. So let's look at a very schematic way at the difference. What sort of, we're now thinking about mathematical models. What do we have to do to somehow understand these phase transformations, microstructure, whether we can do energy conversion? We have to think about the free energy. So a conventional martensitic phase transformation might look roughly, this is highly schematic, so in the material I was showing you there were 6 Martensite wells, but if you looked in, these are, as you lower the temperature, this would be a very schematic view of the martensitic phase transformation. So these would be the wells of martensite here, there would be the austenite well, and as you raise the temperature, you go through this exchange of stability that's typical of a first order phase transformation. If you have an ordinary magnetic material, even what's called giant magnetostrictive materials, they also actually have a second order phase transformation, and they also have a strain, strain or magnetization. So they actually have a second order. So there is a strain. That's what we're going to call in these lectures anyway, ordinary magnetostriction. So the magnetic domains have slightly different strains, and that can be the basis of some interesting effects. So if you now try to combine martensite with ordinary magnetism, it gets a bit complicated. So you have the energy wells like this one, but you also have the second order phase transformation associated with magnetism. So this would be a case where we magnetically order there, and this is what, going from this well to this well, which are extremely close together, but nevertheless there, we would call that ordinary magnetostriction. But of course, you can then jump from this well to this well, and so forth. So we have to model this stuff. Often this ordinary magnetostriction is neglected, and in some of the things I write, it will be neglected. So we have to combine martensite and magnetism, so it's not so easy, and there's very, very little known mathematically about these models, but basically, using, again, I'll discuss a little how this is done, but the basic schematic, there's an exchange energy term, I guess it's written there. Again, even the modeling of that term, and whether the gradient should be with respect to the Lagrangian variable x or to the variable y is a matter of debate, very difficult to decide actually. The free energy should depend on the deformation gradient. Again, we've condensed out all these shift vectors, and magnetization. But the magnetization lives on the deformed configuration. So the way I like to write it is with composing that with the deformation and temperature. And then if you have an applied field, you have a term like this. This determinant is just to take care of the change of variables. And this is the demagnetization energy. This is related very much to what Peter was discussing this morning in terms of depolarization or polarization effects. That's this. It's the L2 norm of HM, and where do you get? Yeah, and HM is the gradient of a potential, and there's a differential equation which relates that potential to the magnetization. So this is like Laplacian zeta is divergence M. So this is there's a well-known theory for this linear equation. So, a unique solution of this equation with, say, zeta in H1, and then you compute the field this way, and you compute the energy this way. I'll tell you about what this means. Now, also there's a symmetry issue, because. And maybe I have that here. Okay, the schematic is then what we expect is we have a reference configuration. We deform it with this deformation y of x. On the deformed configuration lives this magnetization, and it can have domains. So we can have martensite plates like we've seen before. We can also have within those plates, we can have vector field which represents the magnetization. So it's a bit complicated, but and then there's the symmetry part. So it turns out, again, I'm using these circles, but now the circle, we collect two sets of variables: the transformation stretch matrix and one of the magnetization vector, and this would be the easy axis of magnetization, which goes with variant 1 unstressed, because these are the bottoms of the energy wells like before. So anyway, there's a symmetry where if you rotate both of them, you get the same value of phi, and that gives rise to this structure, similar to what we said before. It's just we have now a magnetization lying on there. So let's discuss a little bit this free energy. So there are its minimizers. The microscopic picture is not so different from what Peter was discussing, except in magnetism we usually model the spin of the electron by discrete dipoles. So there are discrete dipoles on lattice points. That's the picture of Lorentz, the simplest picture of ferromagnetism. And what happened, and now let me discuss a little bit the symmetry. So there's a symmetry group, a point group, in the simplest case, a group of rotations. It could be if the austenite phase is cubic, this could be the 24 rotations which map a cube to itself. And under these transformations, you send phi to itself. And there's always a plus or minus here. So if there's a well with plus M1, there's a well with also with minus M1. So you double the number of wells in magnetism. The second thing is this special relation with the point group, and I'll discuss the implications of that. So okay, so the only thing that I need to say a little bit more about is this term. This is extremely important, and again, there's a connection with what Peter said this morning. It's calculated in the following way. It's a lattice. We want to calculate the energy of a lattice of dipoles. So we take, there's the field of a dipole. I guess Peter may have written that down this morning. And if we want to understand. There are two fields in magnetism. There's the B field, magnetic induction, and the H field, magnetic field. For a dipole, the way to think of the H field is this field given here, the field of a dipole with dipole strength D. And the way to think of the B field is you cut out, it's like singular integrals in math, is you cut out a region around the dipole. And you smooth across the dipole, if you want to think of it that way, and you arrange this m star to be so that this combined quantity is divergence free. So if you let r go to 0, this would converge in the sense of distributions to HD plus a direct mass at this. So that's okay. So that's the sort of precursor to the B field. Now we take a dipole at infinity. We imagine we take a dipole at infinity. We bring it in from infinity. We stick it right there. And now we take a second dipole from infinity, right there, and we bring it in. Now, this second dipole, when we bring it in from infinity, it interacts with the first dipole. And so it requires work to bring the second dipole and stick it on that point. And now, does it matter how we do this? We could do many different paths to that second point. And it doesn't. And it doesn't matter if I twist it as I go around and I put it on that second point. It's a conservative force field. So, so the work done in bringing that dipole from infinity to that second point, you can calculate. Okay. Now you bring the third dipole. Of course, the third dipole has to fight against both the first one and the second one. But you can figure that out. And then you populate the entire lattice in that way with dipoles, and you derive the formula. And the formula is not that complicated. It comes out to be that. So that's the energy of a lattice of dipoles. Of course, I should have intersected that with omega, but it's just quadratic function in the dipole strength on the lattice points. L is that lattice. Okay, very good. And now we're going to homogenize this formula. First do that by extending, D is just a constant, it's defined on the lattice points, you extend it as a piecewise constant function. And then you take and you scale the lattice by epsilon. So you scale the unit cell, and you scale this D field by epsilon. So you shrink everything, and you compute the energy by this formula. And you know, if M epsilon converges to M strongly, then you get this formula, and this is exactly the demagnetization term I had earlier. This is typically a constant in ferromagnetism because it has constant length. The length of the magnetization vector is taken as constant. This is a lattice sum that really does come out of homogenization. It's usually lumped in with other terms in the energy. So this is the exact formula you get. And you also get the differential equation. So that's where, so I hope at some level, I mean, I haven't explained it in great detail, but I hope at some level that explains the terms that were originally in the energy I had, which was where? Right there. So that I hope that explains that term. The other terms were lumped into here. This is the applied field. This is a small term, which is the exchange, smooths everything a bit, and that's the free energy, which has this complicated energy well structure. Okay, so that's what we get to work with. Okay. So we can see, it's helpful maybe to see some predictions. So here's something you can do, a very simple thing you can do. That was a symmetry of the energy well. So if U1 and M1 define one energy well, then and you take Q, an orthogonal transformation in the point group of the austenite phase, so maybe a rotation matrix of a symmetry operation of the austenite, then and you do this operation on the U and you do this with the same Q on the M, you get another energy well. Now, many of these Q's have square identity, and so assume that for a second, and then let's look at our compatibility equation. So we know how to solve this now, or we certainly wrote lemmas about that, and there's two solutions, and so we know that if we arrange take one of those two solutions and compute the R, and we have a compatible domain structure. And I hope you have a feeling for what that looks like in the deformed configuration. Here we're in the reference configuration. Now, of course, the M is composed of the Y, so we have to look in the deformed configuration. And in this domain where we have RU2, we have to put, with the same R we got from this calculation, we have to put RM2. And M2 was determined from M1, so it's very rigid. And in this domain, we're stuck where we have to put. In other words, the energy well structure is telling us a lot about what, given the strains or given the deformations, telling us where the magnetizations have to be. That's the way it is. And then there's a tremendous magic, because when you do that, and if Q squared is the identity, these are automatically divergence free. The difference of these vectors dotted with the normal in the deformed configuration is exactly 0. Okay? So somehow if when you realize that, you realize you really can do something with phase transformations and magnetism. Okay, so for example, here's a real case, a nickel manganese gallium alloy, and there's the picture of the domain structure with realistic lattice parameters in the Martensite phase. That's a layered structure, and you're looking in the deformed configuration. So what my point is that these vectors are on the exact energy wells. In fact, these vectors point in certain particular crystallographic directions. This in a certain direction in this variant, and this in the corresponding direction, or a corresponding direction in the other variant. And it turns out that the difference of those dot product to normal is exactly 0. So even with large deformations, you have this wonderful compatibility of the strains implies compatibility of the magnetizations. And then you can, by changing the volume fraction, of course, you can have an actuator, and so that's ferromagnetic shape memory. There it is experimentally. It's not our main goal. Here's another example which can at least convince you there's something to the theory. So we take U1 and U2 and we make this structure. So here's an interesting calculation. So you start with U1 here, and suppose these are compatible wells. Then from what we said this morning, U1 is rank 1 connected to two matrices, precisely two matrices over here. Take one of them. It is rank 1 connected to precisely two matrices over there. So of course U1 is one of them, but the other one turns out to be R2 squared U1. And this one is rank 1 connected to 2 over here, so it must be another one. So you can zigzag across these wells. And this is quite generic. You can do this in many cases. And then, so what does that mean? That means we've satisfied the compatibility conditions, the rank 1 jump conditions across these variants. And now I can add the magnetizations, and consistent with the energy wells. And so once again, there's no divergence, no poles on any of these walls. And actually the deformed shape looks like this. It's a quite nice way to get a large bending shape by using this zigzagging across the energy wells with compatibility. But there are some poles here. There's the jump and the magnetization, dot product, the normal. There's divergence on this interface, a lot of divergence. So in fact, we had a hard time, producing this microstructure till we realized what we should simply do is put little magnets there and get rid of the poles. And so we made a little device like that. And then sure enough, we saw those nice triangles like that. And we're drawn by hand in the magnetizations. These are the magnets you see there like this. There's actually some little substructure in there. And that's understood as well. That's another story that I won't go into. But this has extremely small deformation, but it shows up clearly. But there's okay, more story. I can't tell you the whole story. Just to show you that that these properties change abruptly at a phase transformation in this material, this nickel manganese gallium, that's this material in fact. These are magnetization versus the applied field. So this is an experiment where you have a specimen and you apply a strong field and it magnetizes. And magnetization is a vector field on the deformed configuration, and you take the volume average of it, and that's what's on this axis. You measure that versus field, and this is the austenite phase, and it's about the same if you measure it along 3 crystallographic directions. So the austenite is quite soft material, and now if you compare these two field, the scales on these axes, the magnetization of the martensite is incredibly non-isotropic. It's very different. It's a very hard material. It's hard on the very easy to magnetize on this axis, but a different axis is very hard to magnetize. Again, it's just to illustrate that the properties of the two phases magnetically can be very, very different. Here's a picture. Now, what time did I start? I started at 12. Okay, so I have to finish soon. Okay, so too bad. Okay, so I'd like to show you just something. Now, you could imagine that in a magnetic material, you have all these magnetization vectors. They produce a field. That was that demagnetization term I discussed. So you could imagine that the whole situation is completely different. What determines the microstructure? So this is a material that is been detwinned. So it's a single variant of the martensite. It's strongly magnetic. So does it affect, for example, the austenite-martensite interface? And somehow it seems to have very little effect, because here is an austenite-martensite interface. Oop. Now what's really interesting, you can see the branching, by the way. What's really interesting about this picture is now this is austenite. This was heated up. So we started with a single variant of martensite. So we started in the low temperature phase, and there was some other variants that didn't get detwinned over here. But anyway, most of it was single variant martensite. And then we heated it. And so we saw the austenite come down from the top. Now it's all austenite. We saw the austenite come down from the top, but the presence of the austenite, and you saw like a pretty typical austenite-martensite interface. The presence of the austenite caused microstructure in the martensite. In other words, in the disappearing phase. So that shows how strong compatibility is. It creates microstructure in the phase, not the new phase, but the phase that's disappearing. So anyway, it's the magnetism has very little effect on the other things I told you in the lectures. Okay, I guess I really have to stop there, and especially with, is that right, Anya? 5 minutes for questions? Okay, very good. I'll stop there.
Like if you could just go back to the last video.
Okay.
We had it's like a single variant of martensite, but on the right hand side this is like
Okay, so we weren't completely successful in detwinning it. This is single crystal of one variant of martensite, and in fact it's twinned. This is a rank 1. There's a rank 1 connection with another variant. So this part is messed up with other variants, and but anyway, most of it is single variant, and yeah, so it's just an incomplete detwinning, but it was mostly that variant. Yeah, that's all. Yeah.
And could you do this also with magnetism? Would you expect the same?
Oh, can I? Okay, so that can I field induce the phase transformation? And so if I kept the temperature the same, can I apply a field and get the austenite? Not in this material, because it would be very hard, maybe with very strong fields, but in other materials it'll be quite easy, yeah. And that's the basis of the energy conversion in ferromagnetism that I'll discuss, is the effect of field on transition temperature will be an important part of that, yeah. But not in this particular material. The magnetization, the saturation magnetization in martensite and austenite in this material are almost the same, but the anisotropy is very different. So if you're not familiar, anisotropy in magnetism measures the difficulty of rotating the magnetization vectors away from this preferred axis that was in any of these pictures, like I showed here. This picture's here. I try to rotate that. This is quite a hard material, but hard magnetically. So that's that's the case. So you could maybe have an effect, but it wouldn't be so strong. It would be difficult. Maybe it's even seen. Yeah, you can see that the saturation magnetization of the austenite and the martensite are not so different. So this one is around 60 something, and this is maybe 70, 80. That's so close that it would require very large fields to field induce the transformation. Yeah.
Another question for the other picture, the ferromagnetic one, is this one?
Which one? What was the?
Just the other direction, 31.
Oh, there was another one? Okay.
Like the question would be like, like in your...
No, I didn't.
That was another video, but just like the picture. Like
oh.
Like this one.
Yeah.
So like we had like this bend structure.
Yes.
But I didn't get, is it bent from the very beginning?
No, it starts out straight. It starts out like this theoretical picture. It starts out as a straight beam, and then you push it into this device with the magnets. You just push it and it curls around and develops this. Yeah, that's what happens. So you kind of push it into those magnets, and they each pop in. Each of those domains pop in, and yeah. So you kind of push it right in this region, push it right into there, and then it develops this, and you see. But without the magnets, it's quite hard to do, because it's not so favored. You know, if you want to try to bend it, it's not easy to to create this microstructure generally, yeah. And this goes way back many years. We tried to produce this. This seems to be the easiest way, yeah, yeah.
Other questions or comments?
Well, actually, I had a question about, you were showing the phase transitions that were non-repeatable, right?
Right, yeah.
Yeah, so I was wondering, if there's anything that is repeatable, maybe like in an average sense. Like you can't say, okay, from one cycle to another, I know it's going to happen, but after 100 cycles, I expect, some sort of consistency in an average.
Yeah, probably there is something like that. I mean, I would say that there's, the sort of some gross measures like volume fraction of variant that has 12 variants, volume fraction of variant 7, that's clearly not the same from cycle to cycle in any sense. There's work on this movie actually by Giovanni Zanzotto and a student, and I forget her name. Anyway, they take the view that they analyze the pixels of this movie, and when they turn on and off from austenite to one of the martensite variants, and they think of these as avalanches, and they write scaling laws for these, the number of avalanches of a given size, those kind of laws. And this is what people do with avalanche, with avalanches, with earthquakes, with financial markets. It's a very standard thing to do, is to do these statistical distributions and look for scaling laws. And they find an incredible, I think it's over something like 7 or 8 orders of magnitude, incredibly good scaling law with absolutely linear relation. And they interpret it, so I'm not sure I buy it or one way or the other, but they interpret this as saying that this material satisfying the cofactor conditions is very easily able to adjust to many different boundary conditions or many different situations. It has great flexibility in switching to accommodate a new situation, which is every cycle is new, of course. Yeah. So they have some words about that. I don't know how predictive those types of things are, but they're very interesting to look at for sure. And there's work like that. That's the closest I know to what you're thinking, I think. Yeah. Yeah. Yeah.
And just to follow up, are there any practical implications when you're talking about something like energy conversion, to this non-repeatability?
No, I don't know. What's really needed for the energy conversion is just being able to every cycle the same. The transformation temperature, you don't want to migrate, and you want repeatability. You want not part of the specimen to die, after cycle 1 million, and so it's really the reversibility, repeatability of the material that's needed. That I don't know. No, I don't know whether there would be any interesting implications beyond just general scientific interest in this non-repeatability. Yeah, it was very surprising to us. Yeah, yeah.
So if I look at the energy which has both monetization and information,
Yeah.
there is exchange there.
Right. Yeah.
And did you try to lose it, maybe relax it, and because then the problem becomes a little bit easier as far as I understand.
Yes, of course, all this analysis I did, I just dropped exchange, these kind of simple domain structures. I just simply dropped exchange, these arguments here.
And
these interfaces
I understand that.
could be smooth. I mean, these would be smoothed interfaces if you had exchange.
It actually makes sense to drop exchange because, looking at the size of...
Yes, yeah. Yeah, that's right. And, there could be a great difference between, there's many questions of that type we don't know. So in this picture, for example, let's see, this picture, so we expect something like, here's a wall between two martensite variants, or here's a wall between two martensite variants. within a Martensite variant, we can also have magnetic domains. That's what's illustrated here. So there's really two types of two very different walls. One is the intervariant wall, and then domain wall. And you know, the modeling of exchange is mostly concerned with this domain wall. So there's many things about this and how we should model this. And even wall models, completely unknown. What kind of wall model would be reasonable for these phase interfaces?
Did anybody look at the model without exchange? Because then you can locally minimize Biffle monetization. I mean,
Yeah, that's what we do. I mean, the calculations I do with just a drop exchange. Yeah, and of course you could have presumably sharp interface, but you know, from a mathematical viewpoint, there's not even an existence theorem for this energy. There's no existence theorem because of this m of y of x. That's really nasty. And if you tried to get rid of it by looking at the deformed configuration, you'd end up with something very nasty in this equation. So you'd nonlinear. You know, if you try to put deformation, you work on the deformed configuration, then m would be very happy. You know, very nice. This you could use the inverse deformation maybe. But this would get really, that linear equation would be no existence theorem for the linear equation actually in that case, because you don't know anything. This would end up with a grad y transpose grad y in it somewhere here. It would be really, really nasty. So there isn't even an existence theorem for this kind of energy. Yeah.
Time for the break. So I'll come back in 8 minutes or then we'll come back in 8 minutes.
Okay.
45, but I think there's beer coffee outside. Thank you very much.
Yeah, thank you.